small group here today. It's interesting because there's 40 people in this class and 30 can make this time. That's another issue, is that, and this is our regular class because it's our substitute regular class, but it was only to be for those 8 people. There were 8 or 9 people that couldn't make, this time. But that's why we're doing all the videotaping. But what seems to be happening is that there's about 20 people who can show up who are just saying,
I think they prefer the video over coming on. I think they prefer the
I
video.
don't think so, because that video takes it's taking 2-3 weeks to show up.
It's a Friday.
Yeah, it's because it's Friday. I mean, I don't know. It's just the way. I never went to class much when I was a student, so. Yeah.
So you understand.
You didn't have to go to college.
But like I said, at my school where I went, it was kind of like, the professors were so insane anyway. It was in the math department that you couldn't get much out of it anyways. You might as well just learn on your own. And then there's the huge classrooms with 200 people in them, so no one really knows whether you're there or not anyway, so no one cares. So it's a different environment. But this is a teaching school. This is supposed to be for giving students a lot of attention. Okay, so we have you have basically those 2 tests we talked about, integral test and we had, comparison test and limit comparison test are sort of lumped together, but you have 3 tests there. So the integral test, positive, decreasing, continuous functions. If the integral will converge if and only if the series converges. Limit comparison test, very strong test, but you have the 3 cases of the limit comparison test. Does everyone understand the cases of the limit comparison test?
We should go over
More information.
So, yeah, so what you're doing is you have your series Bn, you know something about. That's your known series. And you're being asked, well, does series An, does it converge? And you take your known, and if you're dealing with positive terms, okay, so you're going to take a limit, and you're going to take this limit as n gets big of an divided by dn. And when you're doing that, 3 things can happen. It'll either be 0, infinity, or it could be a positive constant, greater than 0. So case 1 is, it turns out to equal a positive constant. Okay, so case 1 is, we'll just write it out like this. So case one is you take this limit and it's a positive constant. Now that gives you full information. So whatever series Bn did, series An is going to do. If this converge, this will converge. If this diverge, this will diverge. You get full information. Okay? So full information. If and only if. All right, now in case 2, what if this limit is infinity? Well, if that's happening, the ANs are larger than the BNs. So if the series BN diverged, then something larger than it would diverge. So you would get information in that case. However, if the series BN converged, well, just the fact that the ANs are larger, they still might converge or they might diverge, you don't know. You can't really tell. So you only get information, you get partial information. And in other words, if the series BN diverged, then your unknown one will diverge, the one you're asking about. But if it converges, you'll get no info. So you'll only get information in this case. So if you were to do that, what would you do? Let's say you tried a limit comparison test and you chose a known divergent series like 1 over n, and you did a limit comparison test with it, you ended up getting infinity, what would you do? Panic or what would you do? Would you abandon the limit comparison test, or what else could you do?
Well, can you continue? Because if BN diverges, then so will AN. Can it still diverge as the answer?
Oh, I'm sorry, I said, what if it converged? So let's say you took 1 over n squared. We're in the infinity case.
Then change your BN?
Yeah, you could change it. In other words, change it to 1 over n. Maybe you picked 1 over n squared. So yeah, so let's say you picked series 1 over n squared, which converged. Okay. And you did a limit comparison test. You were asked about series AN. And you did a limit comparison test. You got a infinity. So what would you do at that point? You might try another test, but you might also just say, well, I'll try a different known Bn as maybe I'll try 1 over n or something that diverge, right? And try it that way, okay? So don't abandon it immediately, that's what I'm trying to say. And similarly, what happens if you got 0? So if you got 0, again, here you would get partial information. And if your series Bn converged, then you would get convergence. Because the ANs were smaller compared to the Bn. So again, in this situation, if you had started with series 1 over n or one of your known divergent series, and you ended up getting 0, the fact that your A sub n is smaller than 1 over n doesn't really give you any information as to whether that series is going to converge or diverge. You could just switch your choice. You could try a known convergent one. Or you could try a different, one altogether. You could try whatever you want and just try a different example. Or go to another test. Go to an integral test if you could. Go to any number of tests, a ratio test. We haven't done that yet. But you will at the end of the class we're going to add on like 3 or 4 more tests. So you don't have to give up, in other words. I think the ratio test is actually the next test coming up. Yeah.
So how do you pick the Is there like a
How do you
low
choose?
head-to-head?
Yeah, well, I think that you have to kind of develop an instinct for it, but I don't think it's totally obvious all the time, but on a lot of them where you're dealing with so one polynomial like divided by a polynomial, those situations that we talked about last time, you would pick it on the basis of the leading powers. Yeah. Or you might pick it as to look at, kind of filter out some of the information that you're looking at that you feel is less relevant somehow. I think we saw an example of that, like with the 1 over n over root n, and there was like a -1, and the right. So you might look at something like this. I think we had a problem like this. And you might just kind of filter out that information and say, okay, well, I'll do a limit comparison with 1 over n root n, right? Really easy if you have a situation where you're going to have, like we said, like you might have some extra information that's not as relevant because it's less power, so it could be like 9x to the 6 plus 10 or whatever. This information is not as important as what's going to be happening here. So if I had like an n to the 14th, let's say, and then I could have like 1001 n to the 12th. This information, etc., is not as important as what's right here. And so you might just choose this series and just use that as your known with a limit comparison test. So some of it's instinct, some of it's, just your knowledge of the p-test. It's also your knowledge of where your knowledge base is at this point, right? I think you're just starting, so it's not like you have so many known ones anyway. But you might, this one as your known divergent series, and this one as your known convergent, they'll be pretty good in a lot of problems. I'd say that you're going to use limit comparison tests just as probably for homework problems, they'll be pretty good.
Can we do an example problem?
Yeah, so let's do some more examples. Or actually, any of the p-tests are good. So you have all of these to work with. So when p is greater than 1, you know that it's going to converge. It's going to be the same thing as the integral test because you could use an integral test with these. And when p is less than or equal to 1, it's going to diverge. So you have all of these to work with. Those are good. But depending upon the specific problem, you still have to be a little creative sometime in how you visualize the problem and how you decide which one to choose. So let's practice both integral tests, and let's practice some integral tests, and let's practice some limit comparison tests and comparison tests. I think for the most part, you'll use the limit comparison test more than the comparison test, because if the comparison in most cases, if the comparison test is going to work, then the limit comparison test is going to work. But the limit comparison test is a stronger test. However, in those cases, there are exceptions, like with that sine squared, what I was talking about, where a comparison test would be really good. Yeah. So for like sine squared n over n squared, I think a comparison test would be really good for this series. Whereas a limit comparison test wouldn't be good because sine squared over n doesn't have a limit. But you could use a comparison test and just say that this is less than 1 over n squared, and you know that this the series 1 over n squared converges, so you could say convergence here by just a comparison test, and that would be better than doing a limit comparison test. But for the most part, the limit comparison test will be better and stronger and more effective. Okay, so let's try some more examples. Again, here's an example, and you could kind of see it. I'm looking at number 34, for instance. The square root of n over n squared plus 1. If you're thinking about it, convergence is going to depend upon the tail of the series. And when you're using really big numbers, when n is getting really large, so when you think of n going to like a million, a billion, is adding this 1 all that significant? No. So you might kind of filter that out, and that might give you a hint. Just imagine it's not there. And then what do you think you would want to do a comparison with? You do either a comparison or a limit comparison test.
Can we do n to the power of negative half?
1 over negative half. 1 over like negative half.
Well, can you just do square root of n over n squared?
Yeah,
And then that equals.
but that's 1 over n to the 3 halves.
Wait.
I mean, this is, yeah, I mean, that's the one you want to use, but I don't know where you're getting this negative 1/2.
Where
This
is
is n to the 1/2. This is
N
n to the 1/2 times n to the 3 halves, and so these are canceling. Yeah, 1 over n.
Yeah.
So just 1 over n to the 3 halves. In other words, ignore the 1.
Can you do half minus 2? Would that work? Half minus 2?
Yeah, it's n to the minus 3 halves, but that's 1 over n to the 3
Oh,
halves.
yeah. Oh, yeah.
You said n to the minus 1/2.
Oh, okay.
Yeah.
3 half.
So this is, you might see, oh, okay, I'm just going to use 1 over n to the 3 halves and do this one, yeah? And now I know this converges. Why? Why does this converge?
It's root of 1.
And what test proves that this converges? The
Limit?
the integral p test. Yeah, you're using an integral test. It's because this integral, right, it's a positive decreasing continuous function. And that integral converges by the p test. And therefore, this would be a good known series for your Bn. Now, if you did a limit comparison test, you'd get 1, right? It would go to 1 if you did the limit. Or you could do a straight comparison test, because adding this 1, making the denominator larger makes the overall term here smaller. So in other words, you do have 1 over n to the 3 halves larger than root n over n squared plus 1. And so you could do a straight comparison test. So by the direct comparison test, you would get convergence of the smaller because the larger one converged and the smaller one would converge. So you know this one would converge. Either way. And that would be much better than trying to integrate that directly, right? It would be much better to use a limit comparison test or a comparison test. In other words, you don't want to, one of your tips as to when you're going to use what test, if you don't want to integrate something, if it looks like a really messy integration, don't even bother trying the integral test, even though if you could make the integral test available, don't even try it. Just go into the limit comparison test or something else, one of your other tests. Yeah? So, okay, let's try another one. How about,
So what we do if we had a factorial in
factorials are going to be really good with the ratio test.
What's a factorial?
Factorial is, everybody always asks about factorials. It should be like, I thought students learned this a long time ago. But n factorial is, right, it's n times n minus 1 times n minus 2, all the way down to 1, right?
Yeah. Okay.
So you can define it recursively by saying 0 factorial is 1, and then n plus 1 factorial is n plus 1 times n factorial. Okay,
Or
so
or 5 factorial is 1 plus 2 plus 3.
no, not plus. 5 factorial is 5 times 4 times 3 times 2 times 1 is 120. Factorials blow up really, really quickly. Okay? No. Well, there's going to be factorials.
Oh, no.
Because there's a lot with you're going to see with Taylor series. Taylor series, there's factorials. No, there's going to be factorials. Yeah, there always is. And with the ratio test, the factorials, the ratio test will probably be the test of choice when you have factorials. But we'll get there. We could do some examples today. I'll introduce the ratio test and show you the ratio test. It would be a good test for.
Can we go over all of the tests?
Yeah, we'll go over all the tests and then we'll do also the ratio test. So,
Before you erase it, how did you get 3 over 2?
oh, because this is n to the 1/2, this is
Oh.
n squared, and I basically ignored this. I
Okay.
said this isn't that relevant, so that's how I chose. Yeah. The same as n to the 1/2 over n squared is the same as 1 over n to the 3/2.
Oh.
Just that was a good thing to compare it to.
Okay.
Yeah, for that reason.
Okay.
Okay. So,
It's just basic.
I can't register for my class
Manipulation.
because I haven't.
I just want to hear the weight limit.
You can register for classes. This one is
Yeah, so this
You can register for
multiplying,
classes also?
then
I'm trying, but.
okay, here's one.
and here's
ln n. So here's n equal 1 to infinity of ln n and root n, and then we're going to put We're gonna put e to the n down here.
Oh,
So what's your thinking with that? Now, if the e to the n wasn't there, what if you just had this? What would your thinking be there? Let's just ignore the e to the n for a second.
ln
The denominator's larger?
is larger.
Hmm?
The denominator is larger.
Okay, well, that just gets you past the divergence test. The series, the sequence that generates that series is going to go to 0. But what about this series? What would you know about this automatically?
The pizza.
So what would you know about this automatically? Well, let me ask you this. If it's not automatic, what's your answer to this? What about this one?
Diverge.
Diverge. So what would this one do?
Diverge.
Yeah, it would diverge by the straight comparison test, because this would be larger than this, certainly after a certain point.
Oh, because
Right.
ln of n is larger than 1.
Yes.
Okay.
So this would be larger than this, so this would be diverging. So you could look at this and say, oh, okay, well, if I just had that, but adding the e to the n in the denominator, what's your intuition about going to be as far as that's concerned?
It's also,
No.
it's going to converge.
Converge because of how fast this denominator is going to grow. In other words, and how quickly these terms are going to approach 0. This will converge. I mean, that should be your instinct. This is like really, when you put that in there, that's like really powerful. Okay, as far as going to force that thing to converge. Okay, but you still have to nail it down. What? I don't think you necessarily want to integrate it. So you probably want to do like a limit comparison test. So what do you want to use with the limit comparison test? Like what would you use with the limit comparison test?
1 over n squared.
Wait, can we use the limit comparison test and cancel out ln n and square root of n? Since you're multiplying together. Can we do that?
Just
Is it possible to multiply by the reciprocal and then cancel out?
no, you can't change the problem.
No, but you know how you have to multiply an over bn? So in doing that, can we cancel out terms?
Oh, well, you have to come up with a known. I mean, you have to come up with a known.
Like we know ln of n over square root of n, right? And if we divide it, wouldn't it?
So are you saying to use like you're saying to use something like root n over ln n?
Yeah.
Is that what you want to use? Yeah, but you're doing a division. You're not multiplying.
No, you multiply that to an.
Well, tell me what your choice is. I
Okay.
mean, what's your known? You got to come up with a known. Your choice. If you want to do a limit comparison test, you have to come up with a series that you know something about. And I would suggest that you make use of this.
But don't we know what ln n over square root of n is? We decided
Yeah, but
that
this is diverging. But this whole thing is going to converge. So you want to come up.
Oh.
You should come up with a known convergent.
Okay.
And I would say you got to make use of this. this isn't as important as this.
Because it's working against us. It's trying to diagram and we want to.
Because that is gonna be forcing those terms to get incredibly, I mean, ln grows really slowly compared to when you put this here. So this is really exploding down here in the denominator, which is gonna really, these terms are gonna, remember, it's the speed at which they go to zero. They're gonna get really small, really quick. So when you do the summation, it's gonna converge. That should be the instinct. But what would you wanna use? You could use something with,
One
you
over
could use
each
something
end.
that, you wanna try that?
Yeah.
Okay, yeah.
Oh, 1 over e to that.
Okay, let's try it. Okay, so let's try 1 over e to the n. Now this is a known convergent series. Well, let me ask you this. How do you know it's convergent? How do you know? What test proves that it's convergent?
P-test?
Not a p-test. P-tests are only for x to the constant. This is an e, this is the exponent, this is e to the, in other words, this is e to the minus n, but what test could you use here? Integral test, yeah, you could integrate. You could integrate 1 to infinity of e to the minus x dx. What's the antiderivative?
Is there a difference between the p-test and the integral test?
No, the p-test is the integral test applied to functions that look like 1 over x to the p.
Is there a difference?
The integral test is a general test.
But is there like a difference in terms of application? In both cases, you just integrate it, right?
Well, they're different. I mean, this is saying we want you, if this integral converges, this series will converge. That's the purpose of the integral test. The general test, we're using e to the minus x here.
Mhm.
The p-test is just a way of knowing whether which of these integrals converge.
Oh, that's what you're saying when p is greater than 1.
Yes.
Oh, okay.
It's
Oh,
a
that's what I thought.
specific, the p-test is a specific to those functions. But what's the antiderivative here?
Negative from e to the
Minus e to the minus x. And then we're going from 1 to t, and t's getting big, right? So we're getting minus e to the minus t minus minus, so plus e to the minus 1. And then this is going to go to 0 when t gets big. So when t gets big, this is going to converge. So because this converges, this will converge. So therefore we know that this converges. Okay? Let's limit compare it with that. And let's see what happens. So if we take a limit as n goes to infinity of ln n, ln n over root n e to the n over 1 over e to the n, what happens? Right? And then you just stuck with this limit. And who wins?
that.
This wins, so this is going to go to 0. Right? And you could do L'Hopital and you'd easily see it goes to 0. Yeah.
But this one is before by canceling out the terms
Hmm?
with the n.
What?
You know what I said before? You should try to cancel
Yeah,
out the terms.
well that's, you want to
Yeah.
cancel, but you picked the wrong term.
Yeah.
You want to cancel these.
Drink some more.
So because then this goes to 0.
Yeah.
And now you're in case
1.
3. You're in
Oh,
the
okay.
third
Yeah.
case. So you're in the case where you have a known convergent, and when you took your limit, you got 0. But that's good. That gives you information. That gives you convergence here. Okay? So that's good. Okay? So we did get converged. Yeah? And so, and this goes to your question, how do you know what to choose? I think you were trying to get some kind of cancellation, but it was actually the opposite. What you should have been working with this one as the known convergent one. But that's, again, that's why you practice the problems. I think you'll be better at getting that feel as to what to use in a limit comparison test once you practice more.
So you choose the E, the hidden factor, because
We
that.
choose this because we knew this converged.
Because we-
And we also knew that it's the most important information from this that you can extract from this one. In other words, I claim that this is getting so big so fast compared to both of these that these are not as relevant as this. So when you kind of look at that, you can kind of see this. In the same way that when you look at this, you just focus right here and you don't focus here. Okay? So, but that, you'll just develop that as you go, the more problems you do. But yeah, this was an easy limit comparison test, but I think the hard part is figuring out that you want to use 1 over e to the n.
Yeah.
Yeah.
That's what I wanted to say.
Can.
Okay, let's also practice our integral test. So,
That was the inverse, right?
well, we did a limit comparison test. There was an integral test embedded in there, but I also want to do some problems, straight integral tests. Okay. I can't even read that in my eyes. I think that's an N. I think that's an N. Okay. Series